Welcome to the part 5 of the rice mapping in Bhutan tutorial series, and in this part we'll look at some of the sampling, modeling and validation parts. So this chapter is very heavy on technical content and will require your careful consideration. So in part 4 of the video we saw that we exported some of the composite for the year of 2020. Let me bring this down, and we have those composite for each of the sensors and also the indices from each of the sensors. So you can go to your composite image collection and start looking at several images that's available in there. So in this lecture, we'll learn about some of the modeling strategy, how you can adjust your parameter space and how you can determine the best parameter for your model, and also perform some of the post-processing, common post-processing steps. And if you have data sets, then you can also do an independent validation. At this point, I want to highlight that this red box is where we are focusing our effort in this lecture. We did some of the pre-processing as we saw in our previous video for Sentinel-1 as well as for our optical imagery. Once those post-processed images were then reduced to a single image using the indices and other techniques, we are now ready to use those composite to do the modeling. So in this rice mapping example, we'll be doing random forest model that comes out of the box in the Google Earth Engine code editor. And then in the next chapter, in the next module, we'll look at the validation step. So that means this assumes that you already have collected sample data for the training. We used Collect Earth Online in order to collect the sample data and use those data to train the model. And there is a lecture, there are materials on Collect Earth Online that you can go ahead and look at that if you haven't already have your sample data ready. If you also have some independent validation point, this exercise will also show you how you can test those. For our sampling strategy, we use Collect Earth Online to collect the sample points. Here I have an example that focused on Paro. Paro is one of the most productive district in terms of growing rice in the country of Bhutan. And if you further zoom in and look at one particular plot, so this this brinjal color that you're seeing box is a 30 by 30 meter box, which is called as the plot in the Collect Earth, and each of these points are the sample inside the plot. So you can see 9 sample points inside a plot, and when we label the data, we collected the label for each of these points, and I'll show you how this is linked back to the sampling strategy that we're doing. So if you're not already familiar with Collect Earth, if you go to collect.earth, you should be able to see the website. It's a system that allows you to use satellite images in order to collect your data and interpret your results. You can open Collect Earth. If you have some of the project, you can go and look at the project. You can also create one. There is also a lot of materials that available, video materials and also manuals that you can use in order to learn more about the Collect Earth Online system. So moving on, I just wanted to show some of the indices that we used for our final composite. So we have NDVI, NDWI, SAVI, MDWI, NDBI. the tassel capped indices, VVVH, the ratio, and the normalized difference on the VVVH. In addition to that, we are also using some of our topographic variables like the elevation and slope. So in this first part, we'll look at the parameterized model.js script, and we'll see how that script can help you grid search your parameters. So let's head over to the code editor and start looking at the code itself. And open the script parameterized model.js. This script will make use of the composite that we generated in our last exercise. As always, as we've seen before, the input needed block is where you will make most of your changes. And if you remember, I showed you there were 9 sample points inside of plots for the collect earth online sampling strategy that we used, and LT2 to LT7 is if 2 or more points were selected as rice, we consider the entire plot as rice. For LT3, if 3 or more were considered rice, we consider all the plot as the rice. So in this way, we have 6 of these sampling points that we have identified. And I'm not gonna go into detail why we selected LT2, but based on some of the experiments we did and looking at the test results, we determined that the LT2 was performing best for our case. And this also is more discussed in detail in our upcoming paper, which should be out very soon. But nonetheless, LT2 is the sampling points that we'll be using in this module. And print the table. There's a column that's called the presence underscore LT2. That is the label that tells us whether a particular plot is a rice or not. If you run that, okay, so you might have to limit this to a few points. Let's limit that to 10 points. We'll fix other issue later as we go through. And here you can see that each of these have a property called presence underscore LT2, which tells us whether that particular plot is a rice or not. Now the other error that we need to fix is fixing our path to the composite, and we do that over here. In our previous exercise, we generated the composite for 2020. We'll use the same. So in order to get the path to that, you can just click and copy this image collection ID from clicking this icon here. So let's go and yeah, so that is the path. We already have composite 2020, so I'm just gonna remove that. Now we have the purple path, and if you go and look at the individual image, so Landsat indices 2020, and you can open the individual image inside that image collection, which will give you the path to that image. So this is the path we want to construct, and we are using the path variable here to do that. So path variable stores the path to the image collection, and that path is being utilized over here. So we're loading indices images from different sensor, Sentinel-1 images. We're also loading our topographic variables from the SRTM, slope and elevation, and finally constructing our final image by adding all these images together as a single image with multiple bands. So if you go ahead and run that, you should not see any error, hopefully. Yes, so the final imagery is printed out, and the final number of training bands is printed out. The final imagery has NDVI, Sentinel-2, brightness, and all the indices that we saw in our previous lecture, and the list are printed over here in training bands. So using 29 elements to train our model, and in the next data points block we are actually going and looking at our sample points. So it looks like we have total of 5,000 samples spread throughout the Bhutan, which you can also see in the map over here. So this shows your rice point as green dots and then non-rice as a red dot. The total number of rice points are 1300, non-rice point are 1896, ratio of 1.6 rice to non-rice ratio, and it's just showing the same information in a histogram. Then in the sampling block we are sampling our final image with the training points that we collected using the label. Our label here is presence_LT2. We are using a random column seed so that we're getting same results every time we're conducting this experiment. So it's just showing the total number of points. So you see some difference between the points because in some places where it's very highly cloud cover, those pixels are maxed. As a result, the training points on those maxed pixels are removed. So we altogether we have almost 5,000 points. So this is where the fun begins, and this is where you can customize, because sometimes when you run a task you might get an error, and I'll show you how to do that. So this is where we will generate our search space. We have number of trees, variables per split, all these variables that goes into the random forest model. So if you go to the docs and search for random forest, you'll see a small random forest classifier that takes number of trees, variables per split, minimum leaf population, bracts, fraction, maximum nodes and seeds. You can learn more about what each of these parameters mean here, but for now I'm gonna create the search space for each of these variables that we can play with. So number of trees, the search parameter goes from 40 to 120 in an increment of 10. So if you print this, and run this, yeah, so we have a list that starts from 40, goes up to 120 in an increment of 10. So that is what's going on here. So similar thing for other variables here. For max node we are only using 1, which allows the nodes to sprawl without having any limitation on how many nodes it can get. And so in this way we would generate altogether of 540 different models, and it takes a long time. So you'll have to export the results so you can look at it offline and also try to determine the best parameters from the parameter space. So now our final parameter space is a dictionary where each of these variables are defined. And then finally we'll create the random forest parameter space. We're passing the training samples, the bands that we'll be using, our final imagery, the label, and the parameter space. And this is the random forest parameter space function inside the model module. So if you go to model.js, I'll go in a separate tab here and open model.js, and search for the function. Here's the function, you can see. So inside this function, what is going on is whatever the feature collection or the training samples that you provide, it's just gonna split that into 75% and 25%. The 75% is used for training purpose and the remaining 25% is used for the testing purpose. It's again printing the same thing, number of samples, rice sample, non-rice sample, generating those histogram again, testing samples, number of rice test sample, number of non-rice test sample. That information you can see here. So you have of 4,995, 3,722 are used for training. Of that sample, maximum are the rice sample, and there are less non-rice sample. Same is the case with the testing samples as well. So basically it grabs all these parameter space and then run each of these model by creating a combination of these parameters, and at the end it calculates the importance for each of these model. It would also then create your error matrix, the test accuracy, kappa, recall, precision, F1 score, all the fun stuff, and then returns the results back to you. So this is where you will get the results, and we are wrapping that in a feature collection so that you can easily export in a CSV format. And in the next line of block, this is where we'll export the results from each of these models. And if you go to your tags, you'll see a random forest. This is the name of the label, presents underscore LT2 2020. And if you run this, so this will be exported in your Google Drive inside the folder called the Earth Engine. Then this is the file name. So run this and we'll come back and look at this file in our next lecture.